In this video, I'm going to be talking about the definition of a subspace. And I will talk about a couple of examples of things that are subspaces and things that are not subspaces of Rn. Specifically, this is going to be subspaces of Euclidean n space, not some abstract vector space, which is something that we will deal with later in this course, but not today. And remember that when I say Rn, I mean the set of all n tuples of real numbers, which we can kind of interpret as the set of all n-dimensional vectors. Okay? And we'll be talking about subsets of Rn. Okay? And one thing that I will point out that I'm not sure that I've used this notation in this class is that if we talk about, some kind of subset of the real numbers, I could say if W was equal to the interval 0 to 1, W is a subset of the real numbers, of the set of all real numbers. Now we'll say that a subset of Rn is a subspace if that subset contains the zero vector and if it is what we would call closed under addition. If you take two elements that are in the space and you add them together, then you stay in the space. And so we call that closed under addition. And then the other thing it needs to be is something that we would call closed under scalar multiplication. And that's that if you take a vector that's in the space and you scale it up or scale it down by some sort of constant, multiplying it by some real number, then that new vector will still be in the space. Okay, so it needs to be closed under scalar multiplication. And in this part of the course, scalar is going to mean real number, but there could be a situation later on where scalar could be something that was something beside a real number. But for now, we're just looking at, our spaces are going to be Euclidean n space, and our scalars are going to be real numbers, at least for the time being. All right, so I'm actually going to start with kind of an example. Credit to, I think it was 457 in my sixth period class. So he said, is this like kind of like a cube inside of a bigger cube situation? I was like, no, but that's an interesting place to start. And so I actually really like that. We're going to say, suppose W is a cube of some kind in three-dimensional space. That seemed to be what this student was implying when he asked me that question. So, I'll just say that that big box in black is all of R3. And then W is this cube. Okay. Well, one thing that I know for sure, if it's going to be a subspace, then it's going to need to contain the origin. So I'm just going to pretend that the origin is right there with that green dot I put down. Okay. We'll just say that that's the origin. Well, if that's the case, then I can go over here, and in red, I'm going to draw a vector. Let's call that A. Okay. A, we'll say maybe it comes from the center and goes to kind of that edge of the cube. Okay. A is an element of W. A is contained within the space W. Okay. But then if I go and I consider what happens to 2A, right, that looks like it's about 2A. 2A is not in W. Meaning that this cube thing, is not closed under scalar multiplication. Okay. Now what that means to me is that these subspaces need to be kind of infinite in some sense. Okay. And so I'm going to draw you a picture of something that is a subspace. But definitely, if we need to be able to multiply by any real number, we need to be able to multiply by really large real numbers, really large negative real numbers. So we're going to need it to be, in some sense, pretty big. All right, now this is pretty clearly the graph of y is equal to 3x. It's a little wiggly and couldn't get a very straight line down, but this is the graph of y equals 3x. Okay, we can look at this red line as a subset of R2. Okay, and so I'm going to call this red line, I'm going to call it W. I'm going to give an algebraic specification for W as well. I'm going to say that W is equal to the set of all vectors in R2 for which the second component, what we have in the past interpreted as Y, okay, is equal to 3 times the first component, what we had previously called X, right? So I'm going to say that X2 is equal to 3 times X1. All right. Now I'm going to tell you that W is, in fact, a subspace. Right? And I will show you how to demonstrate that. Okay. The first condition is the 0 vector an element of W? Well, you can see it pretty clearly is because it goes to the origin, right? That's kind of what we're looking for. So the fact that the 0 vector is an element of W. Okay, well, the 0 vector in our case is, this, where x1 and x2 are both equal to 0. Well, it does fit. 0 is equal to 3 times 0, so I'm happy. Right? Okay, we need to check the fact that this space is closed under addition. I can do that. Okay, I'm going to need to get kind of a generalized version of 2 vectors that are in this space, but I could call it A1 and 3A1. And I could take a vector B and I could call it B1 and 3B1. Okay, A plus B is equal to A1 plus B1 and 3A1 plus 3B1. What you can do is you can say that that's equal to, and then kind of makes it a little easier to see when you put the first one in parentheses. You can factor out and you can see that it fits that pattern where the second component is equal to 3 times the first component. The first component is A1 plus B1 in parentheses, and the second component is just 3 times that. All right, now we need to check and make sure that if we take A and we multiply it by some real number, it's still going to be in W. Well, what I'm going to say is that K times A will be KA1 and 3KA1. Really, it's K times 3A1, but we know that multiplication of real numbers commutes, so we can do this. And, if you really wanted to make it obvious, you could throw parentheses around it and say that it's number and then 3 times that number. So it is closed under scalar multiplication. And since it contains the 0 vector, it's closed under addition and it's closed under scalar multiplication, I can conclude that this W is indeed a subspace. All right, here's another kind of subset of R2 that I'm going to show you is not actually a subspace, but I want to show you how that looks algebraically, how that plays out when something is not a subspace. This is pretty clearly the graph of y equals x squared, right? And so I'm going to let W be the set of all vectors in R2 for which the second component is equal to the square of the first component. Okay, I'm telling you that this is not a subspace. Okay, now, when you're going to prove something is not true, what we need is like a counterexample, basically. So what I'm going to do is I'm going to come over here and find what's not going to work. Okay, I tend to think that this, it's going to contain the 0 vector, but I don't think it's going to be closed under addition or scalar multiplication. Yeah, because whereas 1, 1 is in the space, 3, 3 is not. Okay, so this is really like it's too curved. We'll see that, you'll start to recognize this is linear algebra. So things in general should probably not be curved. But What I'm going to say is that I'm going to give you a couple of reasons why this is not a subspace. W is not closed under addition. Okay. Uh, let A equal 1, 1. A is in W. Let B, or maybe I should actually won't use A and B because in the past I've been using those for like generalized vectors. V1, V2 is equal to X is -1 and Y is 1. Okay, so we've got that. And we've got V1 plus V2 is equal to 0 and 2. And that's not in my space. Okay, so it's not closed under addition. That's a problem. And I could also say that, if V1 is equal to 1, 1, 3 times V1 is equal to 3, 3. And that is not the thing where the second component is the square of the first. It would need to be 3, 9. So this is another reason why this is not a subspace. It's neither closed under addition nor closed under scalar multiplication. It would need to be both in order to be a subspace. Okay, I think that's going to be all for this video. I've shown you the definition of a subspace, an example of something that is a subspace, an example of something that is not a subspace. I think that'll probably